Hello, my name is Reynolds. Welcome to Mat-073. Today we're going to look at section 8.3. The topic is graphing logarithmic functions and converting exponential functions into log functions and even solving a log function. And one of the main things you should pick up from this video is to undo a logarithm. You do change it into an exponent because they are inverses of each other, which we talked about on the previous video. So again, inverses are every time you see an x, you write a y. Every time you see a y, run an x. That's called a one-to-one function. So instead of y equals 3 to the x, you have x equals 3 to the y, and that's an inverse function. You read this, well, the book says that you read it, the logarithm base 2 of x. I would have read this, the log of x base 2, but the book differs from me just a little bit. But again, I read this log x, it just so happens to be base 2, so log x base 2. This is some nice inverse conversation, but I'll talk more about that in a moment. The main thing, again, that you need to know from this slide is that the inverse function is of an exponent is a log, and the inverse of an exponent is a log, and the inverse of a log is an exponent. So to undo addition, we subtract. To undo multiplication, if you have to solve for x here, we would divide. So to undo an exponent, we would have to take the log of both sides, or to undo a logarithmic function, we'd have to do the exponent. The easiest way to look at this inverse property is through the graphs. So remember, exponential functions go through the point 0, 1 and have a horizontal asymptote at y equals 0 if there's no shift. So for example, if I just had y equals 2 to the x, a point on this, if you let x be 0, well, 2 to the 0 just equals 1. So that's why most exponential functions, if there's no transformations, go through 0, 1. Well, the inverse of 0, 1 is 1, 0. So here comes the logarithmic function over here. And instead of a horizontal asymptote, y equals 0, we have a vertical asymptote at x equals 0 because that's the inverse. And on a previous video we talked about growth and decay. So the same decaying factors that happen for exponents happen for logs. And to refresh your memory, the three things that cause decay are a negative x, a negative a, and a b value between 0 and 1. So to graph our first logarithmic function, I would start here at 1, 0, because logs go through 1, 0, and the log of 1 is 0. And there's no horizontal shift, there's no vertical shifts. You could even write this as x minus 0 plus 0, just to convince yourself that there is no shifting. So the asymptote stays right here at x equals 0, and we have growth because we don't have any decaying factors. So if you would like to do a t-chart, you certainly could, but I think the goal here is just to see the general graph of this. Notice they're introducing something really interesting. The log of 3 base 3 also equals 1. So if you let x right here be 3, the y value will equal 1. So that's a nice point to find on log functions. There it is right here, 3, 1. And the reason why is because the log of this 3, which is the x value, is equal to 1, which is functions are set equal to y. So that's a nice point to find. However, if there's a phase shift, sometimes it's a little bit harder to find that nice point. So I'm going to switch tactics here. If x is positive, we're going to start at this 1, 0 again. This, if C parentheses, go the opposite direction, so we're going to go to the right 4 units, and this says go up 1. So we've done this before with exponents, graphing exponents. So here's a start value. I'll move 1, 2, 3, 4 units to the right, up 1. The asymptote, instead of being at y equals d for exponents, it's always at x equals c. So here's my c, and where I'm getting these letters from is just a general equation, a log x minus c plus d. So I'm talking about this being the c value, this 4. And that's where the asymptote's going to be at x equals 4. So there's that vertical line, x equals 4. And there's no decaying factors. Remember, I'm looking for a negative x, a negative a, or a b value between 0 and 1. None of that exists, so I would have nice growth. If you wanted to find additional points, we could. We could look it on our calculator, but that works generally for me. Again, if x is positive, we're going to start at 1, 0. This time we're shifting 4 units to the left. 1, 2, 3, 4. So 4 to the left, and then 1 down. That's what this tells me. So there's a point on the function. There's a decaying factor right here, a negative a term. So remember, the general equation is negative a log x minus c plus d. So that's a decaying factor. So instead of growth, we have decay, and that means I would start up, oops, let's get this asymptote in here. It would also be at negative 4. 1, 2, 3, 4. So I actually can't be on this side because I can't cross the asymptote. So that will help define where the function's at. So I'll start up high and head down low. And this function gets infinitely close to the asymptote but does not cross. Looks something like this. This one, the start value, again, is 1, 0, because x is positive. I would move 3 units to the right. The asymptote is at x equals 3. And we have a decaying factor right here. The b value is between 0 and 1. So decay means start up high and head down low again. These things flatten out much, much faster than what you might think. If I just go back to the original log function, remember, the log of 10 base 10 will equal 1. So way out here at 10, 1, you can see my graph's off a little bit. There's a point at 10, 1. We could actually look at this on our calculator because your calculator only does base 10. So if you were to type in the log of 10, it will give you 1. You could always just go to your graphing calculators and graph these. It's hard to type in a base of 3, but at least you can see the general form. I haven't shown you how to type in a base 3 yet, but you can see the general form. It doesn't increase a whole lot. Again, on your calculator, it doesn't show you this vertical asymptote and the function getting really close, but it does exist. Here's an example where x is negative. So instead of starting at 1, 0, I'm going to start at negative 1, 0. I'm going to set 5 minus x equal to 0. So negative x equals negative 5, or x equals positive 5, and that means move to the right 5 units. So this says go to the right 5 when I set that equal to 0, and this says go down 3. The asymptote is also 5, right? So and again, this means 5 units right of where it normally is, and it's normally at x equals 0. So there's 1, 2, 3, 4. So there's the vertical asymptote at x equals c. In this case, x equals 5. And I'm going to move this point 5 units to the right. 1, 2, 3, 4, 5, and 3 units down. 1, 2, 3. So there's a point on the function. This is a decaying factor, and this is another decaying factor. I got a negative x. So let's review again. Negative x, a negative a. There's no negative a, but I do have a b value, a base, between 0 and 1. So that's going to be 2 decaying factors, which is going to cause growth. And that means I'm going to start low and head up high, coming this way. So again, it flattens out really quickly. Next, we're going to look at the definition of logs. I like to talk about this being the fishhook. It's really b to the y equals x. This red kind of looks like a fishhook to me. So that's the definition. If you ever see a log, you can change it into an exponent. Just like we can change x minus a negative 5, subtraction, we can change that into addition. And just like if you ever have like x divided by 5, we could also change that into a multiplication problem by just doing 1/5 of x. So we can write multiplication as divisions. We can write subtraction as addition, and we can write logs as exponents because they're inverses of each other's. So convert this into a logarithm form. I'm going to look at the base of the exponent, and the base of the exponent becomes the base of the log. And remember, logs equal exponents. So here, the exponent is 7. So that's what I'm going to set my log equal to. Logs can be written as exponents, so they equal exponents. So the only thing I have left is called the argument, the log of 49 base 7. Is how I'd read this. This next one is similar. I like to start with the base. So the base of the exponent becomes the base of the log. So I'll say log base x. And then I talk about logs equal exponents. So this equals 9. So logs, oh no, the exponent, logs equal exponents. So the exponent is -2. So I'll set the log equal to -2. And the only thing left here is to go with the 9. I could always go backwards, I suppose, and check this with the fishhook method. X to the -2 equals 9. That seems easier for students to process. But here are some answers. I think we did okay with those two. And then here are the fishhook methods, where if we start with 3, we're going to go fishhook backwards. So this would be 3 to the -m equals x. And this would also be a fishhook backwards. So I'll start with the base. It becomes the base of the exponent. Logs equal exponents. So this log equals the exponent 6. So a to the 6th equals z. So again, I'm just converting exponents to logs and logarithmic functions into exponents. Why is that helpful? Because they'll help me solve. If you see a log, I'd convert it into an exponent by doing the fishhook. So 3 to the -3 equals x. Of course, maybe you recognize 3 to the -3 as 1 over 3 cubed, which is 1/27. If I do the fishhook over here, I'll start with the base. X to the 2nd equals 4. So I'm just following the start here. X to the 2nd power equals 4. And then I take the square root of both sides. Remember, whenever you take the square root, you get 2 answers, plus or minus 2. So 1/27 was my first answer, and plus or minus 2. Got to be careful of these solutions because you can't take the log of a negative number, and this base has to be positive too. So the solution is only just 2. We have to throw out the negative part of this. It's called an extraneous solution. Even though I got an answer, it doesn't check, because if you look at the graph of logs, they have to be positive, and this base needs to be positive as well. So there's 2 things that always need to be positive: the base of the logarithmic function and the answer. So if I ask for you to evaluate log 81 base 3, we can't do it on our calculators because our calculator only does base 10. So if you were to type in the log of 81, you'll actually get an incorrect answer. So my recommendation for this particular problem is not to convert it to base 10, which I'll teach you how to do a little bit later in the video, but I would set it equal to 81, set it equal to y, and use your definition, your fishhook definition, which says 3 to the y equals 81. And perhaps you know that you can write 81, and if you don't know, you could always do some upside down division. Pick prime numbers, like 3 goes into 81 3 times, 3 goes into 27 3 times. So you could really write 81 as to be 3 to the 4th. So y actually equals 4. We'll try the same thing for this guy. If I just set this log function equal to y and try the fishhook, 3 to the y equals 1. Oh, I know 3 to the 0 equals 1. So this answer must be 0. And we know that anyways, because all log functions go through the point 1, 0. So I should have known the log of 1, that's the x value. So the log of x equals y. Well, if x is 1, y is 0. That's a point on all log functions. The last one is a little bit more complicated. Let's set it equal to y. So the log of 1/9 base 3 set equal to y, and I'll do the fishhook again. So 3 to the y equals 1/9. You can write this 1/9 in terms of base 3. Let's bring it up to the numerator first of all, and then I'll change it to a base 3. That's 3 squared which means 3 to the y equals 3 to the negative second. So this is kind of a neat property. It's called the 1-to-1 property. If 3 equals 3, then these exponents have to be equal in order for the left side to be equal to the right side. So I'm not dividing by 3. I'm just saying, hey, if yellow equals yellow, pink must equal pink. Called the 1-to-1 property. So, yep. 4, just looking at answers that the author got, and negative 2. Did we get that too? Yep, y equals negative 2. So again, recapping, all logs, if somebody asks for a log of 1, think about it going through 1, 0, because all log functions go through the point 1, 0. So the log of 1 will always be 0. It doesn't even matter what the base is. And then the log of 5, base 5, will equal 1 as well, because of 5 to the first equals 5 to the first. So if the base equals the argument, then the answer is always 1. So this answer, the log of anything, is going to be 0, and this answer, as long as these things are equal, the answer is always 1. So 0 and 1 for those solutions. You can type these in. If there's no base, it's assumed to be a base 10 down here. So if they don't write a base, it's assumed to be base 10. Be careful, you can't take the log of a negative. Your calculator will blow up and it'll say error message. So make sure you can type those in and get those answers. And here are some other log properties. We've talked about this one already, where the log of a equals 1. I think we've talked about the log of 1 equaling 0. We haven't talked about the last two yet, but I will in the later videos. Well, I guess we talked about the 1-to-1 property a little bit, because we used exponents. So 3 to the 5th equals 3 to the x when 5 equals x. Well, that's for exponents, but that also works for logs, and that's what number 4 is talking about. If I have the log of x equaling to the log of 5, then x has to equal 5. I'm not dividing by log. I'm just saying, hey, if this yellow log equals this yellow log, and they would be equal if they had the same base, I'll put a base 7 in here. So if this was base 7 and this was base 8, then I couldn't do a 1-to-1. But if log base 7 equals log base 7, then I'm convinced that pink has to equal pink, and that's how I make the statement. So this is that 1-to-1 property. If you have any questions, feel free to email me.